Hi there, it's Heath. You from an undisclosed location today. Let's go ahead and get started. A matching intergraph is a set of edges in which no two edges share a vertex in common. Um, so in this graph here, show you a couple of examples. We could match A and B together, C and D, and E and F. That's this matching right here. Um, so I've picked three edges, one, two, three edges, and none of the edges share a vertex in common. This has AB, this has CD, this one has EF. Or we could match them the other way around. We could match BC, DE, and FA, and that's this matching here. We don't have to match everything. Um, this is a perfectly legitimate match, BC with EF. This is still a matching. It's a set of edges. It does not repeat any vertex. It just happens to leave some vertices unmatched. And so this is also a matching, just single edge AB. It matches two of the vertices and leaves four of them unmatched. So the requirement is that a matching cannot repeat vertices. So no two edges share a vertex in common. These sets are not matchings. AB because B and E are matched to different. So this is not a match. And then this one's not a match because they are not edges. AD, there's no edge there. There's no edge from B to E, no edge from C to F. And so can't match if there's not actually an edge between. Those aren't match. That's not a matching. Let me show you a couple definitions. A matching is maximal. It is impossible to add any new edges. Still have a matching. So let's go back to the example we were just hexagon. This is I match these two and these. This matching is maximal. Because I cannot add any of the remaining four edges without repeating. But it's not maximum because I can find a matching with that has. This matching here. So maximal with an AL means I cannot increase the size of this matching. Maximum means we cannot find a different matching that has more edges. Size and width. Okay. And perfect means
every vertex is matched, represented. That's the same thing. Perfect requires that G has to have I have an odd number of vertices, then I can have a maximum match wedges, but it's not perfect because there will still be vertices left over. All right, so let's take a look at this example here. This came from the Harris textbook. Does this graph have a perfect match? I'll give you a couple of seconds to think about this. It does have an even number of vertices, but this vertex in the center has to be matched somewhere. And whichever vertex it matches to, the two disconnected 5 vertices. And I can match some of those 5 vertices, but I'll have one left over. And because there's no edge that connects this vertex to one down here, I won't be able to come up with a perfect. So even though it has an even number of vertices, it cannot match all 16. The most that we can match. Okay. All right. So, question that we want to ask is, how can we tell? As matching. Having an even number of vertices is not enough. It's necessary, but not enough. So we're going to look at this definition. This is going to be part of our answer to the question. An augmenting path is a path in a graph that starts and ends with an unmatched vertex, a vertex that does not appear in its. So this vertex. And in which alternate edges are part of the match. I'll show you an example on the next. So let's look at this graph here. This graph has a matching that only includes the edges. And it contains an augmenting path starting from H and going to A, to B, F, and so it starts and ends at an unmatched vertex. And in between, it alternates between edges that are outside the matching. AH is not in the matching. AB is in the matching. Is not in the matching. F is not in the matching. If we find an augmenting, and here's why it's called an augmenting path, then what we can do is we can toggle all of the edges on the path. We can turn AH on, AB off, on, CF off, F on. By toggling these, we now have a match with 4 edges instead of 3. Because we turned on 3 edges and turned off 2. Find a Burgess theorem says that the matching is maximum if and only if we have no augmenting path. So if we want to test to see if we have a perfect matching, we find a matching, look for we look for an augmenting path. If we can't find an augmenting path, matching we've got is as big as it gets. Can find an augmenting path, we'll augment the path and then try again, continue to find an augmenting. So we either use up all the vertices or we can't augment anymore. That's going to be the idea. So this is an if and only if theory. So we have to prove both directions. This direction is easy, and it's going to be cut by contrapositive. Contrapositive says that if contains an augmenting path, then M is not maximum. The proof, we just saw it toggling along an augmenting path. Size of M, and a maximum matching can't be in. So now we have to look at the other direction. And we're also going to do this by contrapositive. Contrapositive in the other direction is if M is not maximum, then contain augmenting path. Here's the proof. If assume M is not maximum, then there is another matching bigger than okay. We're going to look at all of the edges that are either in M or in N, but not both. Okay. And what we're going to do in a moment is show that S contains an augmenting path. Okay. So here's the idea. Because M cannot repeat vertices and N cannot repeat, then any vertex in S can only have a degree of 2 or less. It can touch an edge in M, but it can't touch more than one edge in M, because M doesn't repeat vertices. And it might touch an edge in N, but it can't touch more than one edge. And so S contains vertices of degree 0, actually just one. Now, there are only two ways that we can build a graph if we only have degree. We could start with a vertex of degree 1, build a path from it, or we could start with the vertex and build a cycle from it. All the vertices. I can't have anything else. A intersection, for example, has a vertex of degree, so we can't have that. So only things that have just degree 1 and never wrap around and cross over themselves. So it's either just going to be a straight line, where it wraps around and itself back at the end, but not somewhere in the middle. 6, because a 6 would. Therefore, there. Cycles, paths. And we can say more, because the cycles it contains have to be each cycle. Here's why. I look at the edges along the cycle. This edge is an M. The next edge has to be an N, because this vertex can't be repeated. That means then that this edge has to be an M, because this vertex is not allowed to be repeated. So then this edge would have to be an N, this edge would have to be an M, this edge would have to be an N. And I have to end with an even number of edges so that when I end, the last edge and the first edge are not part of the same matching. So S contains only cycles and paths. Furthermore, S contains the cycles in S are all equal. But an even cycle would have the same number of edges M and the same number of M. We know that N has 4 edges, because we said right up here that N is bigger. Because N is bigger than N, S must an odd path. It can't be made up just of equal cycles, otherwise N and M. And it has to be an odd path, and since N is the one that's bigger, it will start and end in N and not in M. That will be an augmenting path because it will start and end at the vertex that's not in M, and then it will alternate between N and M. Augmenting. Finishes up. Odd path, because N is the matching that's bigger, has to N. I played with your heart. Sorry. Odd path, bigger, it has to start and end N vertices. Therefore, we have an augmenting path because it starts and ends with a vertex that's not in M, and alternates between edges that are not in M or in M. That's an augmenting. Okay. So this is Burgess' theorem. Burgess' theorem was proved in 1957. You don't know that, but I'd throw that. All right. Let's talk about bipartite graphs for a moment. The graph is bipartite if all of the vertices can be split up into 2 groups. Sometimes we call them X and Y. Sometimes we call them P and N for positive and negative. In such a way that all of the edges in the graph connect one type of vertex to the other type of vertex. That we do not have any edges that go from a positive vertex to another positive vertex. Don't have any edges that those aren't allowed. You can only connect one kind to the other. If we have a bipartite graph, can we conclude that G has a perfect match? Well, the answer to this question is no. And this is an example. We have an odd number of vertices because I drew 4 vertices in only. So we may not have a perfect matching because we might not have an even. What if we have a perfect match and we conclude that the graph is bipartite? That's a trickier question. I'll leave it. So let's look at some examples. Okay. Gotta go back to this definition, but I'm not skipping it on purpose. I'm coming back. So here's an example of a graph that it does not have a perfect match because it has an odd number of vertices. But we do have a matching that is perfect for y. That is, I can match this vertex up here, and I can match this vertex up here, and everybody in y has a partner. But there is a leftover vertex in x. We say that matching is an x matching if every vertex in x is matched, and a matching is a y matching if every vertex in y is matched. So this is a graph that has a y matching, but no x matching. And the reason it doesn't have an x matching in this case is that there just aren't enough vertices in y to match. But here's a graph that has 3 vertices in x and 3 vertices in y, and yet there's neither an x match. Because these 2 vertices in x both want only one partner in y. They can't both have that same partner because we're not allowed to repeat. So there is no x match. And then for the mirror image reason, there is no y matching because 2 vertices. So since the vertices in x and y can't figure out a way to share, there is no x matching or y. Even though the graph has enough vertices to make a matching possible, it doesn't have enough. Hall's theorem gives us a way of testing to see if whether we have an x. If I can find a set of vertices x that is bigger than the set of neighbors, what the capital N is standing for, neighbor set. If there is a set of vertices in x that's bigger than its neighbor set, then we can't have an x match. So the number of neighbors always has to be bigger than or equal to the size of the set for all subsets F. And this is an if and only if condition. As long as we have enough neighbors in every single case, we can build a matching that's perfect for x. Then if we have the same condition on the other side, we can build a match perfect for y. Okay. All right. Take care. Around.